The Whirlpool galaxy spins with elegant, sweeping arms. This same design appears again and again across the cosmos. Why does the universe repeat itself? The recurrence of specific galaxy shapes, from spirals to featureless ellipticals, is not a cosmic accident. It is a fundamental clue to the universe's hidden laws and ancient history. What universal forces sculpt these familiar forms over billions of light years? We will travel from the invisible grip of dark matter to the explosive life cycles of stars. By the end, you will understand why the cosmos favors a limited palette of designs. This journey reveals the hidden architecture that makes the vast universe feel deeply interconnected. What do you think it means to see the same patterns written across the sky? A century ago, astronomers made sense of this cosmic repetition by creating a map. It is called the Hubble tuning fork diagram, and it organizes the entire galaxy zoo into a simple, elegant scheme. On one prong of the fork, you find the majestic spiral galaxies. Picture a colossal pinwheel of starlight, spinning in the void with arms of blue young stars and glowing pink stellar nurseries. It is a slow-motion firework, a self-sustaining cycle of birth and light. On the opposite prong sit the elliptical galaxies. These are not disks but swarms, vast clouds of ancient stars that glow with a soft, golden light. They can be nearly perfect spheres or stretched ovals, like celestial footballs, and they lack the dusty lanes and brilliant arms of their spiral cousins. Then there are the irregulars, the misfits of the cosmos. These are chaotic, misshapen collections of stars, often looking as if they were pulled apart by some immense, unseen force. This classification is far more than a filing system for the heavens. The very fact that nearly every galaxy we see fits so neatly into these categories is our first major clue. It whispers that the universe is not assembling galaxies at random. Instead, it is working from a limited, universal recipe book. The repetition of these forms is a direct reflection of the laws that govern them. So what are the ingredients in that cosmic cookbook? The answer begins with an invisible ingredient that holds everything together. That invisible ingredient, the master sculptor of the cosmos, is gravity. It is the silent, relentless force that has been pulling the universe together since the first moments after the Big Bang. In the beginning, the cosmos was a nearly smooth soup of matter and energy. But it was not perfectly smooth. Tiny, random ripples in density, smaller than a single atom, were imprinted upon the fabric of space. These minuscule fluctuations were the seeds of everything we see today. Over billions of years, gravity patiently amplified these imperfections. It pulled ever so slightly more on the slightly denser patches, drawing in gas and the mysterious, unseen dark matter. What began as a faint whisper grew into a cosmic shout, gathering matter into vast, interconnected filaments and dense nodes, the great cosmic web where galaxies are born. Without gravity, there would be no galaxies, no stars, no planets. It is the fundamental prerequisite, the universal rule that makes structure possible. But how does this single force create such a variety of shapes? The fate of a galaxy is largely sealed by the initial conditions of its birth cloud. Picture a vast, collapsing cloud of primordial gas and dark matter. Its total mass, how quickly it is spinning, and its overall density act as a cosmic blueprint. A massive, fast-spinning cloud will naturally flatten into a disk as it collapses, its rotation preventing it from shrinking into a simple sphere. This is the origin of a spiral galaxy. Within that disk, the same gravitational dance creates spiral arms, density waves that trigger the birth of new stars. Conversely, a cloud with very little rotation has no such constraint. It collapses into a vast, swelling swarm of stars, an elliptical galaxy, where stellar orbits are chaotic and random. The universal nature of gravity ensures that similar starting conditions, even in opposite corners of the observable universe, lead to strikingly similar outcomes. This is why we see the same galactic shapes repeated across the void. Gravity writes the rules, but another, more violent force is responsible for the intricate details. Think of a figure skater beginning a slow, graceful spin. As they pull their arms inward, their rotation accelerates into a breathtaking blur. This is the conservation of angular momentum in action, a fundamental rule of physics that also dictates the shape of a galaxy. That vast, collapsing cloud of primordial gas possessed its own slight spin, a faint rotation imprinted from the turbulent early universe. As gravity pulled the cloud inward over millions of years, this spin intensified dramatically, just like the skater pulling in their arms. The cloud could not collapse into a simple sphere because its own rotation flung material outward along its equator, forcing it to flatten into a vast, spinning disk. This is the direct origin of a spiral galaxy, a cosmic pinwheel born from spin. Within this stable disk, stars form and orbit in orderly paths, and the majestic spiral arms emerge as gravitational density waves. Now, consider a different primordial cloud, one with the same mass but almost no initial rotation. When this cloud collapses, there is no spin to resist gravity's inward pull in any particular direction. It crumples into a vast, three-dimensional swarm of stars, their orbits chaotic and random, creating the smooth, featureless form of an elliptical galaxy. The presence or absence of that initial spin is a cosmic fork in the road, a decision written into the fabric of a galaxy at its birth. This principle of angular momentum is a universal law, acting with the same unwavering consistency from one end of the cosmos to the other. It guarantees that wherever a massive cloud of gas begins to rotate, a disk will form. This is not a suggestion, it is a physical requirement, a predictable outcome repeated across billions of light years. So, while gravity provides the raw material, spin provides the final form. But what happens when these elegant, spinning systems are thrown into chaos by the most violent events in the universe? Galaxies are not built upon empty space, but upon an invisible framework. This cosmic skeleton is made of dark matter, a substance that does not emit light or energy yet exerts a powerful gravitational pull. Think of a modern skyscraper. Long before its glass and steel walls are erected, a massive internal framework defines its ultimate height and silhouette. Dark matter acts in precisely this way for galaxies. It forms vast, diffuse halos that are the true foundations of the cosmic structures we see. These halos were the first structures to condense from the primordial universe, their immense gravity creating deep wells that ordinary, visible matter could not resist. The gas and dust that would become stars simply flowed into these pre-existing scaffolds. The properties of this dark matter halo are the ultimate determinants of a galaxy's destiny. A massive, slowly rotating halo creates a deep, stable gravitational well where stars form in a chaotic, random swarm, leading to the birth of an elliptical galaxy. In contrast, a less massive but rapidly spinning halo provides the perfect cradle for a spiral. Its rotation encourages the collapse of ordinary matter into a thin, orderly disk, where spiral arms can later emerge. This hidden architecture is a universal component, present in every corner of the cosmos. It ensures that the construction process for a spiral galaxy here and a spiral galaxy 10 billion light-years away follows the exact same set of rules. The blueprint is always written in the language of dark matter. Yet this cosmic blueprint of gravity and spin is forged within a crucible of chaos. The early universe was not a placid, serene expanse. It was a violent and churning sea of primordial gas, roiled by immense forces. Shockwaves from the deaths of the first massive stars, titanic supernova explosions, sent ripples tearing through the surrounding clouds. The gravitational tug-of-war from colliding protogalaxies stirred the cosmic pot. injecting a fundamental turbulence into the very substance of creation. This turbulence is a third universal force in our galactic recipe, a chaotic energy that plays a dual role in shaping the final outcome. In one scenario, this churning motion can act as a form of support, a persistent agitation that prevents vast reservoirs of gas from cooling and collapsing too quickly into a thin, orderly disk. It keeps the material puffed up and hot, resisting the quiet settling that spiral galaxies require. In such a turbulent environment, when stars do eventually form, they are born with random, chaotic orbits, leading directly to the puffed-up, swarm-like structure of an elliptical galaxy. Conversely, in a quieter region of space, this same turbulent force can have the opposite effect. The shockwaves can actually compress pockets of gas, seeding the local instabilities that trigger the birth of new stars. It is the difference between a calm lake, where a gentle breeze creates only small ripples, and a storm-tossed ocean, where massive waves crash and churn with uncontrollable energy. The level of this primordial turbulence, imprinted on a galaxy during its formation, becomes a decisive factor. A calm cradle of gas can gently settle into a majestic spiral disk. A violently agitated one is destined to become a chaotic elliptical swarm. This chaotic ingredient is universal, present everywhere, but its intensity varies from one galactic nursery to the next. This variation is a key reason we see such a diverse yet repeating cast of characters in the cosmic play. A spiral galaxy begins its life as a vast, rotating reservoir of potential. Within its invisible dark matter halo, primordial gas, rich with hydrogen and helium, starts a slow and inexorable journey. As this gas radiates heat away into the cold of space, it loses its energetic support against gravity. It begins to cool and condense, flowing inward toward the heart of the halo, but it cannot collapse into a simple ball. The entire system is spinning, and this rotation forces the infalling gas to flatten, like pizza dough spun into a disk. This is the moment of creation for a spiral galaxy's most defining feature, its vast, thin plane of stars and gas. Within this stable, rotating disk, the final act of galactic artistry begins. The iconic spiral arms themselves are not permanent, solid structures. If they were, the galaxy's rotation would wind them up into a tight, indistinguishable coil within a few 100 million years. Instead, they are grand density waves, moving through the galactic disk like cosmic traffic jams. Picture a slowdown on a busy highway. Cars enter the congested area, slow down, and pack together tightly before speeding up again as they leave. The wave of congestion moves far slower than the individual cars. In a galaxy, stars and gas clouds orbit the center. As they enter a spiral density wave, they are compressed and slowed, triggering a burst of star formation. The brilliant blue light of massive young stars and the glowing pink clouds of hydrogen gas outline the wave, creating the luminous arms we see. This is why the spiral arms appear so bright. They are stellar nurseries, lit up by the traffic jam of star birth. The great Andromeda Galaxy, our nearest large galactic neighbor, is a perfect example of this mature spiral structure. Its two prominent arms, sweeping out from a bright central bulge, demonstrate this universal process in action. It is not a unique snowflake, but a classic specimen following the same cosmic rules. For a spiral galaxy to maintain this elegant structure for billions of years, it requires two key conditions. First, it needs a continuous supply of fresh, cold gas, often siphoned from intergalactic space, to fuel new star formation in the arms. Second, it needs a relatively peaceful life, free from major galactic collisions that would violently disrupt its delicate disk. When these conditions are met, the result is a self-perpetuating cycle of birth and light, a common developmental path written into the laws of physics. This is the profound reason we see the same elegant spiral form repeated from one side of the observable universe to the other. The universe is simply following the same reliable recipe, producing one masterpiece after another. While the spiral galaxy thrives on peaceful order, the elliptical galaxy is forged in cosmic violence. Its birth is not a gentle settling, but a cataclysm. Picture two majestic spiral galaxies, each a spinning disk of billions of stars, drawn together by their mutual gravity over an immense timescale. They do not simply pass by one another. They collide. This is not a collision of stars, for the spaces between them are vast, but a gravitational catastrophe. The beautiful, orderly disks are the first casualties, torn apart and shredded by immense tidal forces. The delicate ballet of orbiting stars is thrown into chaos, their neat circular paths scrambled into a random, swarming hive of motion. The result of this galactic cannibalism is not destruction, but a monstrous transformation. The two spiral galaxies merge into a single, much larger entity, a swollen, ellipsoidal cloud of stars. All traces of the original disks are erased, replaced by a form that looks, from a distance, like a colossal, fuzzy football of ancient suns. This is the genesis of a giant elliptical galaxy. A perfect example of this cosmic endpoint is the galaxy M87, a titan at the heart of the Virgo cluster. From its core erupts a famous jet of plasma, a sign of the supermassive black hole that now anchors this merged system. But M87 itself is a smooth, golden glow, a testament to its violent past. This violent genesis explains another defining trait of these galaxies. They are often described as red and dead. The colossal collision that formed them does more than just randomize stellar orbits. It violently compresses the vast reservoirs of cold gas that were the spiral's lifeblood. This triggers a ferocious, final burst of star formation that rapidly uses up the available fuel. Any remaining gas is either heated to such extreme temperatures that it cannot cool to form new stars, or it is blasted entirely out of the galaxy by shockwaves. With no cool gas left, the era of star birth ends. The galaxy is left with only its aging stellar population, whose massive, blue, short-lived stars have long since died, leaving behind the longer-lived, cooler, redder stars. This is why elliptical galaxies glow with that characteristic soft, golden red light. They are cosmic retirement homes, vast collections of ancient stars whose fiery days of youth are far behind them. This dramatic life cycle is not a rare event. In the dense urban centers of the universe, the galaxy clusters, such mergers are a fundamental part of galactic evolution. The elliptical shape is the predictable, standard outcome of this violent but common process. It is the universe's way of taking elegant, spinning structures and recycling them into something entirely different, yet equally magnificent. But what of the cosmic misfits, the galaxies that refuse to fit into any neat category? These are the irregulars, the galactic oddballs that appear as messy, star-forming blobs against the dark canvas of space. The Large Magellanic Cloud, a satellite of our own Milky Way, is a prime example. It is not a majestic spiral or a smooth ellipse, but a chaotic, lopsided collection of gas and stars, looking as if it was pulled apart by an immense, unseen hand. Their lack of symmetrical form is a direct clue to their history. For many irregulars, their shape is a temporary state, the result of a recent and dramatic gravitational encounter. The immense tidal forces from a larger neighbor galaxy can stretch and distort a small spiral, pulling its stars and gas into a disorganized frenzy before it can settle back into equilibrium. In this state of gravitational upheaval, the galaxy becomes a hotbed of star formation, its gas compressed by the very forces tearing it apart, lighting up with brilliant blue clusters. In other cases, an irregular galaxy may represent something more primitive, a cosmic building block that never gathered enough mass or experienced the right conditions to collapse into a mature, stable form. It remains a small, chaotic nursery, a testament to an earlier stage of cosmic assembly. The existence of these irregular galaxies is profoundly important. They highlight that the processes of galaxy formation and evolution are not finished. They are ongoing and dynamic throughout the universe. Not every system is destined for the classic spiral or elliptical path. Yet, even their seemingly random chaos is a predictable outcome. It is the universe's response to specific conditions, like a close gravitational encounter or a lack of initial spin, proving that the same physical laws apply to both the majestic and the misshapen. The cosmos writes its rules in every form it creates. So the Hubble tuning fork is far more than a simple filing cabinet for the cosmos. It might actually be a family album, chronicling the life cycle of galaxies across billions of years. A long-standing and compelling idea suggests this elegant diagram is not just a collection of types, but a potential timeline of transformation. Perhaps a spiral galaxy does not remain a spiral forever. Could it be that the majestic pinwheels and the golden swarms are not distinct, unrelated families, but different stages in a single, universal life story? The central hypothesis is one of cosmic metamorphosis. A spiral galaxy living in peaceful isolation can indeed maintain its delicate structure for eons. But if it has a close encounter, a gravitational dance with another galaxy, its fate is sealed. That collision, as we have seen, violently disrupts the orderly disk, scrambling stars into a random swarm and forging a new elliptical galaxy. In this view, the elliptical is not a different species. It is the elderly, retired form of what was once a vibrant spiral. And what of the chaotic irregulars? They may represent the beginning of this story. Observations from the Hubble and James Webb Space Telescopes have peered back to the early universe, and they reveal a startling fact. Billions of years ago, the cosmos was filled with a much higher proportion of these blobby, misshapen, and intensely star-forming galaxies. The universe in its youth was a place of construction, not order. This suggests that many of these irregulars are infant galaxies, still gathering their mass, yet to settle into the stable, rotating disks that define maturity. They are the cosmic raw material, the proto-galaxies from which the majestic spirals of today will eventually form. This perspective weaves the entire cosmic zoo into a single, dynamic narrative. The recurring shapes we see are not just repeated designs, they are different frames from the same universal movie. A galaxy might begin its life as an irregular, coalesce into a majestic spiral, and then, through a violent merger, end its days as a serene elliptical. This is a life cycle written in gravity and fire, a process that unfolds on a scale so vast it defies human imagination. Yet, it connects every galaxy we see into one great, interconnected family tree. A galaxy's fate is not sealed by its birth alone, but also by its cosmic neighborhood. Think of the vast universe as having its own bustling cities and quiet rural expanses. In the sparse cosmic countryside, the immense voids between the filaments of the cosmic web, galaxies live in profound isolation. Here, a spiral galaxy can spin in serene peace for billions of years. Its rotating disk remains stable, its reservoirs of cold gas untouched, allowing it to continue its slow, graceful dance of star birth. This is the ideal environment for a spiral to maintain its classic form, a testament to a life of quiet solitude. Now journey to the opposite extreme into the dense, crowded core of a galaxy cluster like Virgo. This is a metropolitan center on a cosmic scale, teeming with hundreds or even thousands of galaxies all bound together by gravity. In this urban frenzy, the serene life of a spiral is impossible. Galaxies are constantly brushing past one another, their gravitational fields pulling and distorting each other in a process astronomers call galaxy harassment. These repeated, close encounters can tear away a galaxy's outer stars and, more critically, violently disrupt its delicate disk structure. But the most transformative force in these crowded environments is something known as ram pressure. Imagine a galaxy, rich with cold gas, moving at immense speed through the superheated, thin plasma that fills the space between galaxies in a cluster. This is not empty space, it is a diffuse but forceful medium. As the galaxy plows through this plasma, the resistance acts like a tremendous cosmic wind, forcefully stripping away its lifeblood, the cold gas. Without this gas, the galaxy can no longer form new stars. Its spiral arms, no longer fed by fresh stellar nurseries, slowly fade from view. What remains is often a lenticular galaxy, a ghostly intermediate shape that possesses a disk but no arms, a stalled engine between a spiral and an elliptical. In more extreme collisions, the transformation is total, leading to the creation of a smooth, red and dead elliptical. This environmental pressure is a universal rule, a predictable process that occurs in every dense cluster across the observable universe. It is the reason we find entire populations of elliptical galaxies in these crowded places, while the majestic spirals dominate the lonely voids. The universe, it seems, has a way of stamping a signature shape onto a galaxy based on its address. A galaxy's vibrant spiral arms are not just beautiful, they are a sign of life. This lifeblood is cold hydrogen gas, the raw material from which every star is born. Across the cosmos, galaxies exist within a vast, interconnected ecosystem, constantly exchanging this vital resource with the space around them. They are not isolated islands, but active participants in a grand cycle of cosmic renewal. Think of a spiral galaxy as a great city, its factories constantly producing new stars. To keep these factories running, the city needs a steady supply of raw materials. For a galaxy, this supply line is the cosmic web itself. Vast, invisible filaments of pristine hydrogen gas, left over from the Big Bang, still thread the voids of space. Galaxies that remain connected to these primordial rivers can siphon in fresh fuel, channeling it down to their disks to ignite new stellar nurseries within their spiral arms. This continuous accretion is what keeps a spiral galaxy blue and vibrant for billions of years. It is a delicate balance, however, between supply and consumption. For every new star that ignites, it is only a matter of time before the most massive ones die in spectacular supernova explosions. These deaths are not an end, but a pivotal part of the cycle. The immense shockwaves from these blasts blast heavy elements, forged in the stellar cores, back out into space, enriching the surrounding gas. This galactic recycling is what future generations of stars and planets, and life itself, are built from. Yet these same supernovae can also threaten the very system that created them. If star formation becomes too frenzied, a veritable firestorm of exploding stars can generate powerful winds, violently ejecting huge reservoirs of gas entirely out of the galaxy. This is a catastrophic loss, like a city's factories exploding and blowing their entire supply of raw materials out to sea. Without that gas, star formation grinds to a halt. The spiral arms, starved of new blue stars, begin to fade. An even more extreme version of this occurs when a galaxy's central supermassive black hole awakens, feasting on surrounding material and unleashing unimaginable energy as an active galactic nucleus. The intense radiation and jets from this beacon can heat or expel a galaxy's gas reserves on a monumental scale, effectively sterilizing it of future star birth. This universal tug of war between gas inflow, stellar consumption, and violent outflow is the fundamental regulatory mechanism for a galaxy's life. The ability to manage these resources dictates its ultimate form and fate. A galaxy that can maintain a steady gas supply remains a star-forming spiral, a bustling metropolis of constant renewal. A galaxy that loses its gas, whether from a collision, internal winds, or a voracious black hole, sees its star-forming era end. It becomes a passive, red and dead elliptical, its factories silent, its story of vibrant creation concluded. The shapes we see repeated across the universe are therefore a direct reflection of this cosmic economy, a testament to whether a galaxy is still writing its history or has simply become a monument to its past. Deep within the heart of most large galaxies, a cosmic engine lies dormant. This is the supermassive black hole, a gravitational singularity with a mass millions or even billions of times that of our Sun. For a long time, we viewed these objects as cosmic monsters, devouring all that strayed too close. But a more nuanced picture has emerged. These black holes are not merely destroyers, they are powerful regulators, fundamental to the story of why galaxies look the way they do. When a black hole actively feeds, drawing in gas and dust from its surroundings, it does not consume everything quietly. The infalling material swirls into an incredibly hot, bright disk, and from the poles of this system, it can blast out jets of radiation and particles at nearly the speed of light. This is not a quiet meal, it is a cosmic tantrum of unimaginable power. This outpouring of energy, known as feedback, is the black hole's primary tool for shaping its home. The intense radiation and searing jets heat the vast reservoirs of cold gas throughout the galaxy, or in more extreme cases, blow that gas entirely out into intergalactic space. This is a transformative event. Without its cold gas, the galaxy loses the raw material needed to form new stars. The brilliant blue stellar nurseries in the spiral arms wink out one by one. The galaxy's star-forming era ends, and it begins its transition from a vibrant, blue spiral to a quiet, red elliptical. This process creates a profound and universal link. Astronomers have discovered a tight correlation between the mass of a galaxy's central black hole and the properties of the surrounding galactic bulge. It is as if the galaxy and its central engine grew up together, each influencing the other's development in a delicate, cosmic dance. This co-evolution suggests a universal rule, a feedback loop written into the laws of physics. A more massive galaxy provides more food for the black hole, which in turn, through its violent feedback, dictates the ultimate fate of the galaxy itself. This hidden relationship is a key reason we see the same galactic structures repeated across the cosmos, a signature of a universal process that balances creation and restraint on the grandest of scales. These theories find their ultimate test not in a traditional laboratory, but within the colossal memory of supercomputers. Scientists are now building entire universes from scratch in a digital space, creating virtual cosmos that evolve over billions of simulated years. One of the most ambitious of these projects is known as the IllustrisTNG simulation. It begins with a simple, near-uniform digital cloud, a virtual replica of the early universe. Into this cloud, researchers code only the fundamental laws of physics, the same rules we understand from gravity, fluid dynamics, and the behavior of dark matter. They press start, and then they simply watch. The simulation does the rest. From that primordial digital soup, gravity begins its patient work, pulling dark matter into a vast cosmic web. Gas flows into the halos, cooling and collapsing. Stars ignite, and supernova blast out heavy elements. Entire galaxies are born, live, and collide, all within the computer's memory. The most stunning result is not that galaxies form, but what they look like. Without being given a single instruction on what shape a galaxy should be, the simulation spontaneously generates the entire cosmic zoo. Majestic spiral disks emerge with sweeping arms, smooth golden ellipticals swell at the hearts of clusters, and chaotic irregulars dot the voids. They appear as a natural, emergent property of the physics at work. This is perhaps the most compelling evidence we have that the recurrence of galaxy shapes is not a mystery. It is the inevitable outcome of universal laws acting on dark matter and ordinary gas. These digital universes provide a dynamic laboratory. a place where we can rewind and fast-forward time to witness the precise chain of events that turns a cloud of primordial gas into a familiar spiral, or forges an elliptical through a violent merger. We are no longer just cataloging the shapes in the sky. We are watching them be sculpted in real time, confirming that the universe's limited palette of designs is written directly into its most fundamental code. The most powerful telescopes in the world are essentially time machines. When the James Webb Space Telescope peers into the deepest fields of space, it does not see the universe as it is today. It captures ancient light that has been traveling for over 13 billion years, a snapshot from a time when the cosmos was in its unruly infancy. The galaxies in these images are not the majestic, well-defined spirals and smooth ellipticals of the modern universe. They appear as faint, chaotic blobs, fragmented and misshapen, glowing with the fierce, blue light of rampant, unregulated star birth. Astronomers refer to these as high-redshift galaxies, their light stretched and reddened by the expansion of the universe itself, a cosmic mile marker telling us we are looking back to an era of pure construction. There is no order here, no grand design, only a universe of raw potential struggling to assemble itself. These primordial systems are often small, clumpy, and turbulent, lacking the clear central bulges or symmetrical disks that define their mature descendants. They are the cosmic equivalent of a bustling, chaotic construction site, filled with activity but without a finished blueprint in sight. This is the universe before the universal recipes had fully taken hold. The elegant, recurring shapes we see in our cosmic neighborhood simply did not exist yet. They were still being forged in the fire of those early, dynamic times. The transition from this primordial chaos to the familiar galactic forms we recognize is the story of cosmic maturation. It is a universal process of settling down. Over billions of years, gravity worked to pull these chaotic clumps together. Dynamic instabilities, the same gravitational dances that create spiral arms, began to smooth out the random motions. Gas cooled and rotation stabilized, allowing the first orderly disks to coalesce from the chaos. The very act of observation confirms that the universe has a direction, a tendency toward the stable, recognizable forms that the laws of physics naturally prefer. The fact that we see this same progression everywhere we look, from one deep field to the next, is the final observational proof. The recurring galaxy shapes are not a starting point, but a destination, the predictable and universal endpoints of a cosmic journey that began with chaos and ended with order. Yet even the elegant Hubble tuning fork has its limits. This cosmic classification system, for all its power, is ultimately a simplification of a far more complex and messy reality. Not every galaxy fits neatly onto its prongs. Look closely at a detailed survey of the sky, and you will find a menagerie of cosmic oddballs, galaxies that defy easy categorization. These are the peculiar galaxies, the hybrids and the one-of-a-kind wonders that challenge our desire for a simple universe. Perhaps the most common of these are the barred spiral galaxies. Our own Milky Way is one. In these systems, the spiral arms do not emerge directly from the central bulge. Instead, they stem from a straight, bar-like structure of stars that cuts through the galaxy's heart. This bar is not a permanent fixture. It is a dynamic, self-reinforcing pattern of stellar orbits, a natural instability that can form within a rotating disk. It acts as a cosmic funnel, channeling gas inward toward the galactic center, and often fueling intense bursts of star formation there. Then there are the truly bizarre polar ring galaxies. Imagine a typical elliptical galaxy, a smooth swarm of ancient stars. Now, picture a brilliant ring of young blue stars, gas, and dust spinning around it at a 90-degree angle, like a belt around its waist. This seemingly impossible structure is thought to be the ghost of a past encounter, the remains of a smaller spiral galaxy that was torn apart, and whose debris was captured into this perpendicular orbit. These peculiar shapes are not flaws in the cosmic design. They are vital evidence that the universe is not a static museum of finished products. It is a dynamic, living workshop where new forms are constantly being tested. Every peculiar galaxy tells a story of a recent, specific event, a unique gravitational dance or a slow merger that is still imprinted on its shape. They are cosmic experiments in progress, showing us that galaxy evolution is an ongoing, active process. However, the most profound realization is this: even these bizarre and unique structures are not exceptions to the rules. They are demonstrations of them. The physics that creates a polar ring is the same physics that governs a simple spiral. Gravity dictates the capture of the doomed satellite galaxy. Angular momentum determines the orientation of the resulting ring. Hydrodynamics controls how the gas within that ring collapses to form new stars. The same universal laws, written in the language of mathematics, apply to both the most common spiral and the most peculiar hybrid. This reveals a beautiful truth about cosmic repetition. The familiar shapes we see are not rigid templates stamped out by a cosmic factory. They are peaks in a vast landscape of possibilities, the most probable and stable outcomes that emerge when the universe follows its own rules. The majestic spiral, the serene elliptical, and the chaotic irregular are not the only answers. They are simply the most common ones, the shapes the universe naturally settles into given enough time and the right conditions. The repetition of forms exists within a spectrum, a testament to both the unwavering consistency of physical law and the endless creativity that law allows. This cosmic repetition leads us to a profound, almost philosophical question. Are the galaxy shapes we see truly universal, or are they simply the only ones that could ever produce beings capable of seeing them? This idea is known as the anthropic principle. It suggests that our observations of the universe are unavoidably biased, because we can only exist in a place where the conditions are just right for life. Our very presence acts as a filter, selecting for the specific cosmic environment that made us possible. Think about what life requires. It needs a stable, long-lasting star like our Sun, and a planetary system nestled in a quiet, predictable orbit. It needs a cosmic neighborhood free from constant, sterilizing radiation blasts or frequent gravitational upheavals that would rip nascent planetary systems apart. A majestic spiral galaxy provides exactly that kind of stable, orderly cradle. Its rotating disk offers vast, quiet suburbs far from the chaotic core, where stars can burn steadily for billions of years, allowing planets to form and the delicate chemistry of life to unfold. We do not find ourselves in the violent core of a giant elliptical galaxy, where stellar orbits are chaotic and collisions are frequent. We do not live in a chaotic, blobby, irregular galaxy, still undergoing the traumatic upheavals of its youth. We exist in the calm, structured disk of a spiral, because this is one of the few places in the cosmos where such a long, undisturbed story could ever be written. This perspective does not explain why spiral galaxies recur across the universe, but it offers a stunning reason for why we are here to notice them. The recurring shapes we catalog are not just a random sample of all possible forms. They are a filtered view. We are essentially studying the universe from inside one of its most successful and stable nurseries. The very fact that we can ponder the whirlpool galaxy's elegant arms means that the universe has already performed a grand experiment, and we are living proof of its success. Our own galactic home is heading for a spectacular transformation. The Milky Way and the Andromeda Galaxy, two majestic spirals, are currently on a collision course, pulled together by their mutual gravity in a slow-motion dance that will culminate in a colossal merger billions of years from now. We can already predict the outcome of this cosmic event, a new galaxy that astronomers have playfully nicknamed Milkdromeda. The serene spiral disks of both our galaxy and Andromeda will not survive this encounter. They will be utterly shredded, Their orderly stellar orbits scrambled into a chaotic, random swarm. The resulting entity will be a massive, smooth, and featureless elliptical galaxy, a golden hive of ancient stars. This future is not a unique catastrophe. It is a standard chapter in the life of galaxies, especially those that, like ours, reside in a galactic group. The recurring shapes we see today are merely a single frame in a cosmic movie that is still playing. As the universe continues to age, such mergers will become an increasingly common fate. The serene, star-forming spirals that currently dominate the cosmic census will gradually become rarer, their numbers dwindling as they are consumed by these galactic unions. In their place, the population of large, red and dead elliptical galaxies will swell. This future trend reveals a profound truth about the cosmos. The forces that sculpt galaxies are not relics of a distant past. They are continuous and universal. The same gravitational laws that first gathered matter into spinning disks are now guiding those disks toward eventual collisions and mergers, forever remodeling the cosmic landscape. The universe is not a static gallery of finished artworks, but a dynamic workshop where the same fundamental tools are forever at work, building, dismantling, and rebuilding the grandest structures in existence. But our confidence in this cosmic blueprint is now being tested by a stubborn mystery. Deep within the faint, dwarf galaxies that orbit our own Milky Way, astronomers have found a troubling mismatch between prediction and reality. It is called the too big to fail problem. Our most sophisticated computer simulations, which so beautifully generate the grand spirals and ellipticals, also predict that the most massive dark matter halos in our local group should each anchor a bright, substantial dwarf galaxy. The problem is, we do not see them. These halos appear to be there, their gravitational influence is felt, but they are largely dark, hosting only a few scattered stars or nothing at all. It is as if we have predicted the existence of great metropolitan skyscrapers based on their foundations. But when we look, we find only empty frames or small, quiet cottages where bustling cities should be. This is not a small oversight. If our fundamental understanding of dark matter, the primary sculptor of all galactic forms, is even slightly flawed, it calls into question the very foundation of our story. Why do the same galaxy shapes recur? We have said it is because the same rules of gravity and dark matter apply everywhere. But what if the rules for dark matter itself are more complex than we thought? Perhaps dark matter interacts with itself in ways we have not accounted for, preventing it from clumping as densely in small halos. Or maybe the violent births of the first stars blasted away the gas that should have filled these halos, leaving them starved and dark. This unresolved puzzle is a powerful reminder that our map of the cosmos is still being drawn. The recurring shapes we see are undeniable, but the precise reason for their repetition might hold depths we have yet to fathom. The final chapter on why the universe prefers its limited palette of designs is still being written, one faint, missing dwarf galaxy at a time. These faint quantum ripples in the newborn cosmos were the universe's very first handwriting. We can still read their impression today in the afterglow of the Big Bang, a faint microwave light that fills all of space known as the cosmic microwave background. This ancient light is a baby picture of the universe, taken when it was just 380,000 years old, and it is not perfectly smooth. When satellites like Planck mapped this background with exquisite precision, they revealed a specific pattern of tiny temperature variations, a mottled tapestry of slightly warmer and cooler spots. These spots correspond directly to those primordial density fluctuations, the regions where gravity had just a little more to work with. The slightly denser patches, appearing as cooler spots in the cosmic microwave background, were the cradles of future galaxies. Their specific distribution, their statistical pattern across the sky, was not random. It followed a universal spectrum, a predictable set of rules that looks the same no matter which direction we observe. This consistent pattern means the initial conditions for building structure were identical everywhere. The universe started with the same set of instructions written across the entire sky. This is the profound reason for the cosmic repetition we see. Every galaxy cluster, every spinning spiral, and every elliptical swarm can trace its lineage back to a specific set of those tiny wrinkles in the cosmic microwave background. The blueprint for the great cosmic web, with its filaments and voids, was encoded in that first light. Because the same blueprint was used across the entire observable universe, the construction process that followed had to follow the same sequence of steps. Gravity got to work on the same set of plans, amplifying the same types of overdensities, leading to the same types of dark matter halos, which in turn guided gas into the same types of disks and swarms. The majestic whirlpool galaxy and every other spiral are the mature, fully realized outcome of a construction project that began with a microscopic signature in the first light of time. We are not just seeing similar shapes. We are seeing the final products of a universal recipe that started with the same ingredients and the same instructions everywhere. This deep connection between the largest structures and the smallest quantum beginnings ties the entire cosmos together into a single, coherent story. This cosmic repetition speaks to something far deeper than physics alone. We are not just observers cataloging random celestial objects. We are participants in a universe that operates by a consistent, intelligible set of rules. The fact that a spiral galaxy 10 billion light-years away follows the same blueprint as our own Milky Way is a staggering revelation. It means the cosmos is not a chaotic, lawless expanse, but a realm of profound order and unity. The gravitational dance that orchestrates the sweeping arms of a distant whirlpool is the very same force that holds our planet in a stable orbit around the Sun. The conservation of angular momentum that flattens a primordial gas cloud into a disk is the same principle that guides a spinning ice skater. This connection is both humbling and empowering. We are bound to the most far-flung reaches of space and time through a shared set of physical principles. Our ability to comprehend these patterns, to predict the life cycle of a galaxy we will never visit, suggests that the universe is, in a fundamental way, knowable. We can decode its language because we are made of the same stardust and governed by the same laws. This realization transforms the night sky from a collection of isolated points of light into a single, interconnected tapestry, woven from threads of gravity, light, and time. But how can we possibly map this entire cosmic menagerie? The task of classifying millions of galaxies is monumental, a challenge that has evolved dramatically with our technology. For much of the 20th century, astronomers relied on painstaking manual analysis of photographic plates. They would peer at glass slides holding images of countless faint smudges, using the Hubble tuning fork as their guide to sort each one by eye. This human-led effort built the foundation of our understanding, but it was slow, limited by sheer human endurance. The digital age brought a flood of new data, with automated surveys like the Sloan Digital Sky Survey capturing images of millions of galaxies. Suddenly, the catalog was far too large for any small team of scientists to handle. The solution came from an unexpected direction: the power of the crowd. Projects like Galaxy Zoo emerged, inviting ordinary people around the world to become citizen scientists. With a brief online tutorial, anyone could help classify the strange and wonderful shapes of distant galaxies. This was not a passive activity, it was a global partnership in discovery. The collective pattern recognition of hundreds of thousands of human eyes proved incredibly effective, not just at sorting galaxies, but at spotting the rarest and most peculiar cosmic oddities that automated algorithms might have missed. This human lens provided a crucial bridge, creating a massive, reliable dataset of classified galaxies. Yet, the data deluge continues to grow, and now a new, even more powerful tool has taken center stage. Machine learning and artificial intelligence are now learning to see the cosmos. Scientists can train these algorithms using the classifications made by citizen scientists, teaching the AI to recognize the subtle visual signatures that distinguish a spiral from an elliptical. Once trained, these systems can analyze millions of galaxy images with inhuman speed and consistency, processing in hours what would have taken a human a lifetime. This technological leap is transforming our ability to conduct a true cosmic census. We are no longer just sampling the universe, we are taking a detailed inventory of its vast population. By applying these AI tools to the immense archives of modern telescopes, we are solidifying the statistics of the cosmic zoo with unprecedented precision. We can now say with great confidence exactly how common each galactic shape is, and how that distribution changes across different environments and throughout cosmic time. This is not just about automation, it is about uncovering the fundamental demographics of the universe itself, confirming through vast numbers that the beautiful repetition we see is a rule, not an accident. Our own galactic home is not a solitary island, but a cosmic predator. The Milky Way is steadily consuming its smaller neighbors in a silent, gravitational feast. This process, known as hierarchical merging, is a fundamental rule of the cosmic jungle. The largest galaxies we see today were not born that way. They grew over billions of years by devouring countless smaller systems. The universe builds from the bottom up, assembling great spirals and ellipticals through a relentless series of mergers and acquisitions. We can witness this process in action right on our cosmic doorstep. The Sagittarius dwarf spheroidal galaxy is a small, dim companion to the Milky Way. Right now, our galaxy's immense gravity is slowly tearing it apart, pulling streams of its stars into a vast, faint river that encircles our own galactic disk. This is not a fast or violent collision, but a gradual dissolution, a slow-motion assimilation that will eventually see the dwarf galaxy completely absorbed into the Milky Way's halo. These minor mergers, while not catastrophic, leave their mark. As the shredded stars from the dwarf galaxy are incorporated, they can puff up and thicken the thin disk of the Milky Way. They also contribute to the sparse, spherical cloud of ancient stars that surrounds the main galactic body, a ghostly stellar halo that is itself composed of the remnants of past galactic meals. But when the participants are closer in size, the outcome is far more dramatic. A major merger between two spiral galaxies of similar mass does not end with one consuming the other. It ends with the complete annihilation of both their original identities. The beautiful disks are shredded, their orderly stars thrown into chaotic orbits, and their gas reservoirs violently churned. From this cosmic wreckage, a new entity is born, a swollen elliptical galaxy that bears no resemblance to its spiral progenitors. This relentless process of assimilation is universal. It ensures that a galaxy's shape is not a permanent identity, but merely a temporary chapter in a biography written by collisions. A spiral galaxy's graceful form is a testament to a recent era of peace, while a smooth elliptical tells the story of a violent, transformative merger in its deep past. Every galaxy is a living record of its interactions, a palimpsest where the ghosts of its consumed companions are written in the faint light of orphaned stars. Yet another invisible hand guides the cosmic gas. Woven through the vast expanses between the stars are interstellar magnetic fields, lines of force that stretch across thousands of light years. These fields are incredibly weak, far too faint to compete with gravity's overwhelming pull, but they are pervasive. Think of them as a cosmic fabric, a subtle webbing that permeates the entire galactic disk. Their influence is not in creating grand structures from nothing, but in gently steering the material that is already there. As clouds of cold hydrogen gas begin to collapse under their own gravity to form new stars, these magnetic fields act as a delicate support structure. They provide a tiny but crucial pressure that can slow the collapse, resisting gravity's pull just enough to influence the final size and number of the stars that are born. They also act as cosmic channels. When a supernova explosion sends a shockwave rippling through the galaxy, the magnetic fields guide the flow of the expanding gas, funneling it along specific paths and helping to sculpt the intricate, feathery filaments we see within spiral arms. This subtle guidance system adds a layer of fine-tuning to the galactic assembly line. While gravity dictates the overall blueprint and spin defines the disk, magnetic fields help regulate the intricate details of star formation within that disk. Their presence is another universal constant, a fundamental ingredient found in every galaxy we can study. The recurring structures we see, from the sweeping arms to the dense clouds within them, may bear the subtle imprint of this magnetic handwriting, a final universal ingredient ensuring that the cosmos writes its familiar patterns with both power and precision. The heart of a galaxy reveals its deepest secrets. Journey into the core of a spiral like Messier 77, and you may find a brilliant, searing point of light known as a Seyfert nucleus. This is not just a dense cluster of stars. It is the signature of a supermassive black hole in a state of violent feast. Vast quantities of gas, channeled inward from the galaxy's rich reserves, swirl into an accretion disk so hot it outshines billions of stars, pouring radiation across the entire electromagnetic spectrum. This is the engine of a quasar, the most luminous object in the universe, and it is almost exclusively found within spiral or disturbed galaxies. These brilliant beacons are a sign of a galaxy bursting with the raw fuel for creation. Now, turn your gaze to the core of a giant elliptical galaxy, like M87. While it famously hosts a supermassive black hole of staggering proportions, its center is typically quiescent, a dormant giant. The brilliant, compact point of light is absent, replaced by a smooth, golden glow. This silence is not due to a lack of a black hole, but a lack of food. The violent merger that forged the elliptical galaxy also consumed or heated nearly all the cold gas, leaving the central engine with nothing to consume. The black hole is not dead. It is starved into a state of deep slumber. This fundamental difference in nuclear behavior is a direct and powerful consequence of a galaxy's life story. A spiral's active heart is a testament to its ongoing, gas-rich existence, while an elliptical's quiet core speaks volumes about its violent, gas-poor past. The recurring external shapes we see are not just superficial shells. They are profound indicators of the dynamic processes, or the lack thereof, happening at their very centers. Even our most comprehensive cosmic blueprints cannot account for every structure in the sky. Tucked away in the deep fields of massive galaxy clusters, astronomers have stumbled upon a profound enigma, the ultra-diffuse galaxy. These are cosmic phantoms, spanning distances as vast as our own Milky Way, yet they contain only a tiny fraction of its stars. Imagine a city the size of New York, but with only a handful of streetlights glowing in the immense dark. These galaxies are so faint and puffy that they were almost invisible to our telescopes for decades, their dim light blending seamlessly into the blackness of space. What is perhaps most intriguing is their shape. Some of these ghostly giants appear as faint, wispy spirals, their arms traced by a sparse population of stars. Others resemble bloated, low-density versions of elliptical galaxies. They are not chaotic blobs, but rather faded, recognizable echoes of the forms we know so well. Their very existence presents a serious challenge. How can the same processes that build a dense, star-packed spiral like Andromeda also produce a structure of similar size that is almost entirely empty? It suggests that the fundamental recipes for creating a spiral or an elliptical are incredibly robust. They can operate even when the essential ingredient, the star-forming gas, is in desperately short supply or is somehow prevented from collapsing. These galaxies force us to reconsider what we know about the environments where galaxies form, especially within the violent, crowded cores of galaxy clusters where RAM pressure stripping is most intense. The fact that these faint ghosts still manage to arrange their few stars into familiar shapes is a powerful testament. It reveals that the universal laws of gravity and angular momentum are so persistent, they can imprint order on a galaxy, even when that galaxy is little more than a wisp of its former self. The same physical laws that govern a falling apple also sculpt the grandest structures in the cosmos. Our journey has revealed that the recurrence of galaxy shapes is no cosmic coincidence, but the inevitable outcome of universal rules. From the invisible grip of dark matter halos to the elegant conservation of angular momentum that spins gas into disks, the universe operates from a consistent recipe. This blueprint was written into the fabric of reality at the very beginning, imprinted as quantum ripples in the Big Bang's afterglow. Gravity, the master sculptor, has been patiently following those same instructions for over 13 billion years, ensuring that similar starting conditions anywhere in the cosmos lead to the familiar forms we catalog in our telescopes. This profound order transforms the night sky from a collection of isolated points into a single, interconnected tapestry. It means the majestic whirlpool of a distant spiral and the serene golden glow of an ancient elliptical are not strangers. They are our cosmic relatives, born from the same fundamental processes and speaking the same silent language of physics. Every spiral arm and every elliptical swarm is a testament to a universe that is not only vast but deeply knowable. The next time you look up at the stars, remember that you are witnessing a grand, repeating pattern written across the sky. A pattern that connects our small world to the farthest reaches of space and time. We would love to hear what you find most awe-inspiring about this cosmic connection, so please share your thoughts in the comments below.